All right. All right, we're going again. Okay, tell me what Orchid does.
Yeah, so Orchid is the only company in the world that can do whole genome sequencing on embryos. So what that means is that we can collect 100 times the data on embryos compared to traditional methods. And what you can do with all that data is that you can scan for thousands of different genetic diseases that previously you couldn't diagnose or prevent until after symptoms already emerge and the baby's born. So with Orchid, you can actually select an embryo that's healthy, and so that your pregnancy and your baby, and hopefully that adult baby, also goes on to live a healthy life.
And there's kind of two steps to it, if I remember right. I mean, the parents can come together, get sequenced, sort of see how their genes line up together. And then if you're doing IVF, then you get to also have this information and data on the embryos. Is that?
Yeah, exactly. So we have kind of a really simple way to kind of get the early parts of the information, which is that there's a saliva test. So, mom and dad can spit in a tube, and then they get reports on themselves, but they also get simulated reports on their embryos. So that can be a really useful tool because you might not know, okay, how much can I mitigate risk from this disease by creating embryos? So instead of it being an abstract idea, you actually see simulated embryos based on, you and your partner's DNA. So then you can see, okay, does it make sense to kind of go the old-fashioned way? Am I okay kind of rolling the dice? Or is there, a really large potential risk reduction by actually creating and screening embryos? So it makes that very concrete for parents. And then the part that's really, really cool, sci-fi, first time ever, is that instead of it just being a possibility, we can actually realize that possibility. So we can actually sequence the entire genome of an embryo, which is 100 times the data compared to any other alternative, so that parents can actually select the embryo that actually is lower risk. So this goes from things that are like as severe as a miscarriage or a baby not being able to make it even to that first month of life. There's unfortunately diseases where children don't make it even until kindergarten because there's certain like muscle wasting diseases. So there's really kind of the full spectrum. In a lot of ways, like my mom's condition is much more mild, right? Because she was actually sighted until her mid-30s, and that's when she was diagnosed and the degeneration started. So that's what's kind of crazy about genetics, is that you can have this ticking time bomb that can erupt as early as implantation within the first 20 weeks of your pregnancy, all the way to your childhood, to your early adulthood, to your late adulthood. You never kind of know when those time bombs are gonna erupt. So yeah, the reason why I'm so passionate about the company is like I wanted this for myself. Like the first embryos that we ever tested in the lab were my own, because selfishly I want my kids to not have to go through what I've seen happen to my mom and other folks in my family.
So you have the embryo, and then you take a few cells from it and run this full genome sequence off those.
Yeah. So we're basically building off the shoulders of giants here, right? So IVF itself is obviously like this amazing invention, right? It started out in this sort of experimental and research category, but now it's it's really, really evolved. It's sort of become something that is pretty routine, actually, right? So this procedure of actually sampling embryos has been happening for over 15 years. So when an embryo forms, like day 0, you kind of call it an embryo. Day 5, you call it something called a blastocyst. So it's grown to be about 125 cells, and it's actually, the cells have actually differentiated. So the inner cells are called the ICM, or inner cell mass, and then the outer cells are called something called the trophectoderm. So those trophectoderm cells go on to become the placenta, and those trophectoderm cells are the ones that Orchid actually receives at our lab. So what we'll see later is basically an embryologist taking a laser and actually lasering off. I know that sounds really scary maybe, but those cells are sampled from the trophectoderm, so we get about 5 of them. The crazy thing is that actually, 10, 15 years ago when the sampling started, they actually did it at day 3. So you're talking about taking, a third of maybe 8 or 10 cells, and those embryos actually still survive, shockingly, obviously fewer than today. But yeah, this sampling technique is actually very mature. It's happening, all around the country and all around the world. The real differentiator is just that Orchid is able to get much more data off of that really, really small 5-cell sample. And then that's just historically been the bottleneck, is that, if you want to do whole genome sequencing, it's a commodity on blood or saliva. Lots of different companies can do it, because if you think about it, like imagine, a petri dish, right? You have like millions of blood cells or saliva cells if you think about, breaking those nucleuses open to get the DNA, there's, lots and lots of DNA. So unfortunately, when you have only 5 cells, you have about 30 picograms of DNA. So you have a tiny, tiny quantity. You actually have to copy it over 10,000 times to get that sort of minimum quantity to throw it on any sequencer. So that's kind of really where the Orchid magic comes in, is we, invented a proprietary chemistry or protocol to actually get, whole genome data that's really high quality and clinical grade off of embryos, rather than kind of anyone can do it for, an adult.
Yeah, and I want to ask about all the technology in a second.
Yeah.
On the embryos, okay, say it's a mom and a dad, say it's 2 parents, and maybe one of them, their family has a history of cancer, or maybe both, and that's what they're particularly interested in.
Yeah.
You take these handful of cells. I know you look for a variety of things, but this might be one thing you might do, right? Is then like, how out of these embryos we have, which one is the least susceptible to the thing we're most worried about?
Yeah.
Which might be cancer in this case. Is that the right way to?
Yeah. So basically what's happened over the last 20 years, right? So the human genome was sequenced in 2000, and it was like, cost, over $1 billion. And it was this massive effort just to get the first sequence, right? But then it was kind of like, everyone went silent, because it's like, well, now what do we do, right? So the problem was that it took 20 years to actually go sequence enough individuals where you could actually make sense of these 3 billion base pairs. So what's happened over the last 20 years is that geneticists, researchers, scientists, they've all cataloged thousands of different genetic diseases. So they find all these different typos, they, connect them to, sets of symptoms, and now we're kind of getting a much better sort of molecular map of like what actually causes disease. So, it's kind of crazy. In 2000, if we had this technology, it would actually be pretty useless, because you didn't have that database of, hey, what typos, what mistakes, what spelling errors in DNA, what mutations actually cause disease. But now, because we've had millions of people sequenced at this point, those databases are really rich. So now we know thousands of different diseases. So that's kind of the first step of the analysis, is you get that whole genome data, and then you start looking at, okay, what are the typos, what are the genetic mutations that cause, pediatric cancer, adult onset cancer, birth defects, heart defects, skeletal defects, right? So that's basically the first stage of the analysis is, hey, these are things that, if this typo or mutation is there, that's going to definitively lead to disease. Those are very high penetrance. It's a high likelihood of actually causing a heart defect, causing pediatric cancer. And then sort of the second layer of analysis is something that's even newer, which is called genetic risk scores. So these are more probabilistic models where you're saying, you can't definitively say yes or no, this embryo is going to have heart disease or schizophrenia, but you can say they're at a lower genetic predisposition. So the way that you can think about it is kind of like, well, if you eat Twinkies all day for your whole life, are you at higher or lower risk for diabetes? Obviously higher, because from an environmental or lifestyle perspective, you're making yourself higher risk. So genetics is the same, right? So some people carry a higher or lower genetic load. It's just that previously that's been invisible, right? You know that you're at higher risk because maybe you have a family member and you have empirical odds of, okay, if you have a first degree relative, maybe mom or dad or sibling with a disease, okay, empirically, if you look at other families, a child is twice, 3, 4 times as likely. But you couldn't really definitively say how much for that specific embryo. So that's really what's been unlocked with, now having, millions of people sequenced paired with their medical records. You can build these genetic risk scores or models that basically say, hey, these risk variants make you more or less likely for disease. So that kind of adds an additional layer to the analysis. So, if you're a family that has, a history of schizophrenia or depression or diabetes or, all of these conditions, you previously didn't really have an option besides kind of hope for the best, right? Which doesn't really feel very good.
Yeah.
So what these risk scores allow you to do is actually quantify the level of risk for each individual embryo and each parent. So what that means is that now you can say, instead of being in the 99th percentile of risk, having, 8 times the risk compared to the population average, you can actually move your child to something like the 60th or 70th percentile, which might be very close to the population average risk. So that's kind of what's, I think, really powerful for parents, because they might not want to have a child because they've struggled so much with the condition that they themselves have been a caregiver for, or, they've suffered from, and that's kind of like the primary thing in their mind. So it is just really rewarding to be able to, help those families actually, go do what everyone wants, right? Which is to be able to have a family and to have a baby without that, massive risk hanging over their head. So, In the case of these complex conditions, we can't take the risk to zero, but you are able to quantify the degree of risk kind of based on, all scientific data today, and minimize it. But again, you can't take it to zero. On the monogenic side, you are taking it really close to zero, which I also don't want to undersell because that's extremely powerful.
Yeah. Well,
yeah.
I mean, let's break it into two
Yeah.
categories then. So there's monogenic, these single gene diseases people might think of like BRCA2 or something like that,
Yeah.
where it's we have these very powerful indicators of what might happen
Yeah.
in terms of getting breast cancer.
Yeah.
So when you're doing these tests, how much stuff would fall into that category?
Over 1,200 diseases are in that category. So it's like single base pair typos.
Okay.
Single, yeah.
So you're doing this test and
Sorry, not single base pair, single gene typos, single base pair.
No, say it again.
Yeah. So we scan for about 1,200 monogenic or single gene diseases. Yeah. And we also look at microdeletion or microduplication syndromes, which is, again, another category of typo. But, it's not super interesting to kind of get into the specifics, but the way that you can think about it is that you have 3 billion letters, right? A, T, C, G, right? You break those down to genes. Genes are just segments of DNA. So genes can be anywhere from 1,000 to 20,000 bases. There's a start codon and a stop codon that defines a gene, but you can have typos that are anywhere from single base pair typos to variants of gene. There's all different types. Any different way that you can mess up a string or a word, you can actually mess up a gene, and unfortunately that causes disease. Yeah.
And when you in that category, it's things like what? It's things like cancer.
Yeah. Pediatric cancer. So there's unfortunately diseases have really bad names, right? So there's something called Rett syndrome. It's a spontaneous form of autism that's very severe that affects a lot of females, but. The thing that's crazy about rare disease, it has really bad branding. So there's thousands of these different diseases that are individually exceedingly rare, meaning like, less than 200,000 people, it's how it's defined in the US, have the disease. But if you aggregate them or add them all up, you're talking about actually 10% of the US population. So you're talking about around 30 million Americans are affected by these rare genetic diseases, and 95% of them have no treatment. Right? Think about that. Forget about a cure, right? We have cures to basically none of them, but 95% of them don't even have a treatment. So we're sitting in this situation that's really horrible where, pharma doesn't really have an incentive to even design or attempt to make a treatment.
Right, because they can't sell enough of the drug.
Yeah, so these families are in this horrible situation where it takes, multiple years. Like I think the average time right now is about 8 years to even get a diagnosis, and about 50% of those who are affected are children. So it's this really awful, like isolating situation where you don't know what's wrong with your kid for multiple years, and then maybe kind of in the best case scenario, you just find a support group where really it's just other families kind of like trading notes, but there's not really a way to reverse the degeneration or the disease. So the thing that I think is like insanely powerful and exciting here is that we have an opportunity to, obviously like the polio vaccine was really amazing, and like the smallpox vaccine was really amazing, right? These are like probably like one of the coolest things in modern medicine, but it was just one disease, right? Here, parents have the opportunity to just eradicate thousands of genetic diseases at birth, right? It's like, it's like an insanely powerful possibility that, hey, like this huge fraction of, 10% of, the US population having.
Okay. Okay, so you've got that one bucket where we have this very clear, distinctive genetic evidence of leading to a disease. In these other cases where you're establishing the risk, like where are we today with that technology? How certain is it? People often tell me that things like lots of cancers are so complicated on all the factors that are leading to somebody ultimately getting cancer that it's hard to tell. And so, I was just trying to, what are we telling the people?
No, genetics is super complex. So I think for pediatric and adult cancers, about 10% are in that monogenic category where there's sort of like a severe single gene mutation that, leads, for example, Lee-Fraumeni syndrome, is a type of, pediatric onset cancer. There's a lot of different pediatric onset cancers where there's a single gene that's known. But, we're still learning, right? There's a lot that we don't know. It's because you get genetic screening and it's negative, that doesn't guarantee you a healthy life. It's a risk mitigation strategy, but it's not a guarantee. So what's cool is that you have scanned for, 1,200 plus single gene diseases, and you know that that's not going to affect your embryo, but that doesn't mean there's no chance of ever getting any disease. So similarly for things like schizophrenia or bipolar or Alzheimer's, heart disease, these diseases where it's not just a single gene, but it's actually the cumulative impact of many millions of variants, what you're seeing is a risk score. So essentially it's like, is this embryo in the 99th percentile? And then you kind of map that to the population average. So for something like breast cancer, for example, the population average risk is 12%. And then someone in the 97th or 99th percentile, they might be at 40% or 50% lifetime risk. So maybe a 3 to 5x increase in risk. But that's on top of the monogenic screening, right? So you might be negative for BRCA, but still have a familial risk for breast cancer because you have a relative with it, or just because you individually have high genetic risk for it. Does that make sense?
Yeah.
Is that explaining well? Yeah. So there's basically a monogenic component of risk. That's, I would say, like kind of the first layer of the analysis, and the second layer of the analysis is, whether or not you have high genetic risk score. So that can be for the same disease, or that can be for a different disease, whether or not it's evaluated on the monogenic side. So what that can do is basically just tip the odds in your favor. But again, it's not a guarantee you won't go on to get it. So for example, for me and for South Asians generally, we have incredibly high risk for heart disease and for diabetes. So South Asians are twice as likely to die from a heart attack, and we're much more likely to get them about 10 years earlier than Caucasians or Europeans. So that sucks. I don't want my kids to have to endure that, because even if you're perfectly adherent to medication, right? I don't know if you probably covered some of these startups, but there's entire companies that are built around can you convince people to take their medication every day, right?
Right.
Even after you kind of go through that whole clinical trial of like, okay, let's make this blockbuster drug that actually works. Well, it all falls apart because people don't take their medication every day, right? And that's such a simple intervention, right? Just taking a drug, right? For a lot of diseases, the management or the recommendations are much more complex and extensive than that. But even if you get to something as simple as, okay, like, take your statin, right? Like the vast majority of people, don't actually do that. And the risk mitigation that you can get from embryo selection is kind of, costless in a way, right? At birth, you just don't have to, deal with any type of intervention, hopefully. So just to give you kind of like a ballpark. So for my embryos, I think I had an embryo in around the 95th or 96th percentile, and then I have other ones that are closer to the 70th percentile.
Meaning
so,
95th percentile of
the population. So basically, kind of like if you can think about height, right? Maybe the 99th percentile for men is like 7 feet.
95th percentile more likely to get heart disease?
Oh, so basically, if you were to give a genetic risk score to everyone in the population, this embryo would be in the 95th percentile. So basically, only 5% of the population would have higher genetic risk than this embryo.
I see.
And then you map the percentile to an actual absolute risk. So the absolute risk is different for each disease because, for example, schizophrenia, the average is much lower, for example, than breast cancer. So the average person, like the 50th percentile risk for breast cancer is about 12%. The 50th percentile risk, or like the average risk for schizophrenia, is much lower. I think it's closer to like 1%. Does that make sense?
That makes sense, but then don't you, it's going to be hard. Okay, because you're saying in your case, you're worried about heart disease, and then so you're kind of maybe paying very close attention to that and trying to find the embryo that
lowest risk,
lowest risk, but then you're going to see other things. Like, don't you start having to make trade-offs on what you're going to err for or pick for?
Yeah. So fortunately for us, not quite at this stage. I think that when you're talking about hundreds of conditions, you might get to that trade-off. But just like the way the math works out, it's pretty hard to be like in the top 5 or even 3% of risk for this many conditions. Okay. Just think about it. When you meet someone, like, are they in the top 1% for like multiple, like probably not, right? Yeah. Probably like one thing that's like really unusual or special about them. So it's kind of the same for embryos. Okay. So when it comes to our embryos and like our genetic risk, it's kind of like heart disease and diabetes are the things that on the complex risk side we're kind of mitigating against. And then for the monogenic side, it's kind of the condition my mom has.
And I don't think most people know this, but like if you do something like 23andMe, they're only sequencing about like 2%, the small percent.
Oh yeah. Well, way under 1%. Yeah, it's a tiny array. So
right, and so you're getting this like, it's these very broad strokes about your genes. You guys do a full genome sequence. Why? So I just kept wondering, like, 23andMe has been at this for so long. Full genome sequencing has just been falling in price all the time.
Yeah.
Why were you able to hit on this idea and this technology when some of the mainstream players that already existed didn't go after this? It just seems like it should have been in their heads.
Yeah, definitely. So I think it's kind of just like, what's your use case, right? So I think for 23andMe and Ancestry, the reason why they went with the array technology is because it's kind of a little bit more recreational, right? You only want to pay $100, so then they're like, okay, if you only have $100 to spend, then how much can I sequence? Okay, I can probably sequence 100,000 or 200,000 or 500,000 bases of the 3 billion.
So they're trying to keep it cheap.
So they're trying
for
to
consumers.
make it affordable so that more people can use it. Versus our situation is kind of the actual opposite. It's like it's like the highest stakes decision you're ever going to make in your life, which is which embryo are you going to transfer, right? So, we wanted to give you the entire genome because every single variant matters. It's the difference between, the success or failure of the pregnancy. It's the difference between, childhood onset, a heart defect or skeletal defect or developmental delay or autism or not, right? So it's sort of like in that moment when, you're already spending a lot of money on and time and, energy on IVF, and now you've created embryos, you really want the highest quality possible information. So I think, I don't know, I guess, I don't have a good answer for why they didn't go after it, but it's a very different type of problem, right? There's you have to solve this chemistry problem of how do you get from a really small number of cells that whole genome data? How do you solve the interpretation problem of, hey, now you have so much data, what do you actually do to it? What do you actually present to parents in this specific moment? And I think, solving this like consumer problem of like, how do you get people to buy more, recreational tests is a really different, go-to-market and R&D problem.
And so, okay, if they charge, I think it's like roughly, call it like $120, $150. I mean, how much would your test cost?
Yeah, so ours is $2,500 per embryo, which is pretty much in line with what kind of like a healthy adult whole genome, like clinical whole genome costs. So the thing is like the reason why it's expensive, I mean, I don't want to say it's expensive. The reason why it costs what it costs is that just getting the data off of the embryos is a proprietary process. It's expensive to do that, and then the actual interpretation costs are really high too, right? Because you have a lot of different databases that you have to access. You have actually clinical geneticists that are manually reviewing stuff that's already been, AI or the automated curation services. Again, it's like super high stakes, so you have to have multiple layers of review, right? Something that might be fine on that recreational side of, hey, here's some things that we found. It's not okay on the embryo side. On the embryo side, every single thing needs to be verified, not just by humans, but we actually do something called orthogonal testing too. So basically we use two different types of verification whenever we flag that a variant has been found on an embryo, because again, you're in this really precious situation where you have a bunch of embryos and you don't want to discard or, say an embryo has a very serious mutation if it doesn't. So that's a really serious thing to put that on a report. So we do, confirm through multiple methods that, okay, that variant truly is there. So, that one should be deprioritized for transfer, which again is a really sad thing because you want all the embryos to make it because it's so hard to make all these embryos.
Yeah.
Yeah.
Okay, and so that's on the sequencing side, and then you talk about this unique chemistry from those handful of cells to extract some of this data. That was like another thing that you guys figured out that nobody else had. And how did you figure that out when other people hadn't done it yet?
Yeah. So my background is more on the AI side, more on the modeling. So basically, when you have genetic data, how do you model risk? But we actually pulled in some of the best single-cell sequencing folks from Stanford as well to work on the chemistry. So they had previously been really excited about cancer tumor sequencing because obviously cancer tumors are very, very heterogeneous. So they have a lot of different types of mutations. You want to target therapies to them. And I kind of lured them in a different direction. And I said, hey, cancer is awesome, but what's a really, a spot that's really missing, really, great teams is actually embryos and IVF, right? I think that, having babies is probably one of the most fundamental, parts of life, but, we really haven't seen a major innovation, I would say, since IVF, which happened 40 years ago. So, it was actually, I would say, surprisingly easy to get them excited about embryos because it's like the impact is so obvious, right? It's like, hey, if we get this working, babies don't have to have genetic diseases anymore, right? Obviously, parents have to sign up for it; they have to choose to use it. But I think the impact there was like super palpable. Is like, hey, there's this technology hasn't been updated in like 15 or 20 years. We're still using, really, really old technology to get really low resolution data, just chromosomes, right? So chromosomes, you can think of them as sort of like chapters in a book. So it's like, hey, you got the table of contents versus, what Orchid is doing is, we can actually read every single letter. So like, you wouldn't accept, okay, I'm only going to typo check the table of contents of my book. You'd be like, hell no. No, I need to typo check every single word because, I don't want to embarrass myself by having a typo in my book. But the impact here for your baby is massive, right? I mean, you're talking about a lifetime of, medical bills that are, obviously I'm excited about ASI. I hope we come up with all the treatments. But I mean, I would rather not even have to get the treatment. I'd rather just not have the disease at all. So I think I was, obviously really excited about it, but it was really heartening to see that, the other people who we needed to bring onto the team were also really excited to jump in. And
right here, an Orchid baby.
I need to switch batteries on this guy. So,
Cool.
So cut really quick. Yeah.
Okay. Oh, snoring. Okay. So many questions. Let's see. Tell me. Okay. So you had this team of scientists working on some of the single gene techniques, and then you said you approached this from more of an AI perspective. You're a computer scientist by training, not
exactly.
a biologist or a
Yeah.
MD.
Yeah. Yeah, so that's what's cool. Is basically like computer scientists finally became useful because enough data has been generated that, we can build models and do lots of useful stuff. But yeah, the team at Orchid has both like chemical engineers, software engineers, geneticists. Look, it requires a lot of different experts to kind of come together, to be able to pull something like this off. So
Take that question one more time.
Yeah.
Sorry.
Well, and I was. Hang on one sec. And
if we picked like the epicenter of the house, the most activity.
When we were setting up, and it was so pretty, and I was like, "It'll be okay."
Yeah.
Gone.
Sorry.
Well, tell me like a little bit of. I want your origin story, how you first got interested in this, and some of your background. But I know the very beginning of this was part of your family and what you'd experienced that even got you thinking about this in the first place.
Yeah, I think I kind of only, really understood it as an adult, but kind of, I think when I was a child, it really just felt like this profound sense of unfairness, right? So my mom got diagnosed with this disease after many years, which, unfortunately resulted in her, losing her vision. So she started by losing her night vision, then she lost her peripheral vision, and then as the disease progressed, she lost her central vision as well. And, I think at the time, you just kind of are watching someone that you love have their life and their independence ripped away from you. And you're kind of wondering, why not me? Why not my siblings? Why not, my grandparents who are older? You kind of have this, like, it just feels really, really unfair.
And this was from a single gene.
It's from a typo. So basically, it's not. It wasn't inherited from either grandparent. It was something that was a de novo or spontaneous thing that happened to her.
Okay.
Which is even more unfair, right? Because what are the chances, right? It's like one in hundreds of thousands that would happen, and then why just her? Why not me? Why wasn't it something that affected me as well? And I think that's when it kind of. I think later when I got older, it was sort of like, hey, there's actually this really strange thing going on, which is there's this genetic lottery, and you and I won that genetic lottery. We got to be born, right? Because like a third of pregnancies end in miscarriage, and a vast majority of those are genetic in nature, right? So we won this genetic lottery to even be born, and then we won this other genetic lottery, which is that we get to see and hear each other, right? It's we didn't do anything to earn that. We just got extremely lucky that our genetics allows it, right? And then for my mom, she lost that lottery, right? She lost something that was, really critical to her independence, and there's no way to reverse it. There's no amount of money that can fix it, and
You have this experience. This is all floating around in your head, but you're pursuing computer science.
I didn't really like it. It was something that I that struck me as really unfair, but it was also like, hey, there's nothing I can do about it. And then, when I was doing AI research at Stanford, I was working at a bunch of different labs on like computer vision, different problems, and then kind of by chance, honestly, rotated with a professor who was joined with genetics and AI. So his lab had tons of genetic data. And it was kind of this like really exciting moment for me, because when my mom had been diagnosed like in the early 2000s, there was barely any genetic data. Like genetic sequencing was like in its super infancy, and they kind of had promised, hey, in a decade or 2 decades, there's going to be hundreds of thousands and millions of people sequenced. We're going to like solve all genetic disease, and then those dreams were kind of died because it took so long to actually get that data. And then I was like, whoa, here it is, like just SSH into this folder. There it is. There's like, millions of people who've been sequenced. And that was just like a really exciting moment that, hey, look, now these models have actually gotten good enough. Now you can actually stratify individuals at risk for disease that's greater than monogenic mutations, right? So historically, genetics had just been kind of this pedigree analysis of, hey, here's this family, we're going to find one gene. And it was just aggregating all of these rare disorders. But then there's this like technique that I thought was incredibly powerful, which is, hey, now you can quantify genetic risk for the diseases that are the most common, right?
Is that where, when I first met you, you were about to tell your story. I think you had a sense that some people in the outside world were gonna look at this, from a bit more of a hostile stance.
Yeah.
Because there's kind of two big questions. One is that gets flagged on you guys. One is like, what can you really make of this data on the risk score?
Yeah.
So let's address that one first.
Sure.
I mean, I see sometimes people push back on that, which is like, yes, we have some hints. Yes, we run all these studies, but we don't want to give people false hope that you're saying this is your risk score for this cancer. What does this actually mean? How confident do you feel in that data?
Yeah, I mean, I think it's one of the most well-researched things in modern medicine, right? Like, think about how poorly like nutrition recommendations or the data that's based on, or even a clinical trial, right? You maybe have, 5,000 or 10,000 people at best case in a clinical trial, right? You're talking about hundreds of thousands of people who've been sequenced, and you're seeing, okay, these individuals are at higher and lower risk. So I think it's one of the most well-researched things in modern medicine. And then the other thing you have to think about is like, what is the actual context here, right? So genetic risk scores are already being given on adults, right? And women are choosing to have mastectomies, or basically have their breasts removed and their ovaries removed based on sometimes being high risk there. So that's a huge intervention that's happening on adults. In contrast, in embryos, really you're doing great if you're just doing better than random, right? So providing these genetic risk scores in embryos is a no-brainer, because currently you're choosing randomly. So now you're choosing better than randomly. You're choosing based on, hey, maybe it's a study with 1 million people, maybe it's 100,000 people, maybe it's 10,000 people. But there's a lot of evidence to show that these individuals are at higher genetic risk, and you can validate it very easily, right? You're just testing it on the data. So you say, how many people who are in the 99th percentile actually go on to develop breast cancer? How many people go on to develop bipolar disorder? How many people go on to develop Alzheimer's, right? And you see in every single validation study, not just by our company, but, hundreds of papers on each of these diseases that, they go on to develop the disease at 3 times the rate, 4 times the rate, 5 times the rate. So I think most people would want to know, hey, am I 5 times more likely to develop the disease? Hey, am I twice as likely to develop the disease? So again, it's different than telling someone, hey, you have a disease today. It's a risk estimate. But I think people are pretty comfortable with risk estimates. Hey, they get mortgages, they invest in stocks. It's like, we understand, hey, different investments have different risk profiles. So it's the same thing, right? This embryo is at higher risk. It's not a diagnosis of the disease, but you're carrying more, you have a higher genetic predisposition. And I think that it's not an either or, right? It's not like, hey, if you select an embryo that's lower risk, then all your parenting responsibilities absolved. They should eat Twinkies all day and they're, everything's going to be fine. No, of course not, right? It's like, when your child is born, most people are making the decision of, hey, I want to do organic food instead of, fast food, right? You're making every single decision, which preschool, which there's so many decisions that you make along the way. And if you compare the amount of evidence for those decisions to this, I mean, it's like, there's no comparison, right? Like, there's clearly a massive amount of evidence that supports that your genetics plays a huge role in your health, and then we're just aggregating that here. Of course, like, we have really extensive counseling conversations with our families so that they don't have some sort of false sense of certainty of, hey, when you do this, you're guaranteed a healthy life and unicorns, right? It's sort of like, it's very clear this is a risk mitigation strategy. You do so many things to protect your child from things that could go wrong. There's a huge amount that can go wrong, unfortunately, from genetics, and we're just trying to push the odds in your child's favor. And in terms of the amount of evidence that supports that, I think it's some of the best in all of modern medicine because the N is so high.
When you got into this, I mean, you would have to know. I'm sure you did know. People are going to be upset. Wealthy people are going to get this first, and so they get this edge, right? This is how all types of technology tend to start. You're going to have this like designer baby question, even if it's just healthier babies first. Some people, I think, are still going to have concerns with that, and then it's like, oh, is step 3 now we're selecting for eye color and hair color and intelligence and things like that. I mean, you knew this coming in.
Yeah.
You decided to do it anyway. Like, how do you feel on where this leads in the future? Like, where are you going to like pick and choose what you guys will test for and let people look for?
Yeah, so the way that I see it is like this technology is just totally inevitable and unstoppable, right? Like I don't believe that there's going to be a world where people are going to accept having less information for the most consequential choice of their entire life, right? Like the fact is like the most important parenting decisions actually happen before birth. I would say there's 2. One is who are you going to marry? Who's your partner? And then the second is what is the genetics of your child, right? I mean, there's no bigger difference in the outcome for your child than, do they have pediatric cancer or not? Do they have developmental delay? Are they always going to be, in special needs? Or are they going to be able to go on and live independently, right? And I think that's just like a massive amount of fear that parents are carrying around, and anything that any company can do to mitigate that risk should be supported. So I think when it comes to these other questions about, non-health things, I think it's just a societal discussion, right? It's like, we're not the arbiter of morals, right? Like every single country is going to make different decisions about what information should be censored and what information should be available to parents. I mean, in France, for example, you're not allowed, you have to get a court order to get a paternity test, right? So you can't just, go online and, find out the paternity of, an individual. You have to get a court order. So they've decided in their society, that's what makes sense, right? So I think in every country, people are going to make different decisions about what information should or shouldn't be available, for embryos, right? I mean, obviously different countries have also made different decisions about whether, how much they support like people making families at all, right? In some countries, IVF is fully free until you're like 44, right? Versus in other countries, it's quite expensive, right? In the US, comparatively, it's actually quite expensive compared to other places. So my personal opinion is that, I think everyone who wants to have a healthy baby should be able to have one. And I think that it's unconscionable, honestly, to stigmatize people who want access to this information, right? I mean, we're talking to families who literally had to bury their child before kindergarten, and then to somehow stigmatize and say that they shouldn't have access to this technology so that they can, do the most fundamental thing, which is like to have a family and to have a baby is, I think, insane. But obviously there are people who feel that way, and, I think you can't do anything about that, right? You kind of have to move forward. And like, this is totally the hill that I'm willing to die on because I'm so inspired by those families, and they've already been through so much. And if we can be even a tiny part of, them being able to kind of have the family size, and children who are able to grow up and go on to college, I mean, of course.
If you were a Thiel fellow, which is Peter Thiel, I mean, there are people who are going to be like, oh, this is some libertarian thing. This is this Thiel fellow trying to make super babies. You know, I think, I was doing this research, this Wired story that came out last year. What did they say? Do you remember the headline?
I don't know.
This woman will decide which babies are born. I mean, it's quite dramatic, right?
Yeah, no, it's super dramatic. Well, on the super babies front, I actually totally agree. I think these are super babies. I mean, The most amazing thing possible, I think, for a parent to do is to be able to make their child's life better than theirs, right? And for someone who has seen someone suffer or has suffered themselves from something, and to be able to say, hey, I've been able to take this risk off the table for my child. I mean, of course, that's a super baby, right? I mean, it's insane that, we're all, running around with these genetic time bombs of something horrible that's going to go off. And it's either like a slow burn, right? It's sort of like a slow decay, like my mom's disease, or it's something that's like, super present even in the first couple of years of life. Like, it's insane that we're operating in that paradigm where, okay, we wait for something to go wrong and then we try to fix it, right? It just makes a lot more sense to be able to say, hey, look, from birth, my child's just not going to have to be affected by these things.
It's weird too, because you do, just about everyone has the choice to find out, like, if your child has an extra chromosome, if they might have a chance of getting Down syndrome.
Yeah.
And like most people, I think, do pick to do that, right?
Yeah.
So like all the disease stuff, I mean, that just makes all the sense in the world to me. I think you could kind of see how you get a little freaked out if like Western society or whatever society is favoring, certain genes over others. I don't know, and this becomes like some giant trend writ large. It's not really disease related, but it's more kind of personal preference.
Yeah.
I don't know how I like actually feel about that. I mean, do you know how you feel about that? Are you?
Yeah, I mean, I
you'll
started the company because I'm super excited about the idea of like more healthy babies and like eradicating genetic disease. I think that that's just like a massive mission. There's like so much unnecessary suffering, and it's such a hole in medicine in terms of like no one's even trying to help these families. Like the best they're trying to do is just diagnose them once it's too late. So that's the thing that I'm really, really motivated and excited by. And I think that, all these other questions are, really going to be decided at the government level, the regulation level, right? We're as a society going to decide, hey, what information should people have at this embryo stage? And I think that's how that's going to get decided. But yeah, I think that most parents, I would say, are motivated primarily about having a healthy baby. I don't know. You can tell me what you think parents are motivated by, but I feel like when you talk to parents, that's kind of the thing that's like the biggest fear on their mind, just like, is my baby going to be okay? Are we going to be able to actually have a successful pregnancy, right? There's people who have, unfortunately, recurrent miscarriages through something called translocations, like certain typos, again, in their DNA that makes it so that their embryos don't latch and go on to, result in healthy pregnancies. And like the absolute anguish of like having, miscarriage after miscarriage when you really, really want to have a baby is just, it's like not something I wish on my worst enemy.
Yeah. You look like you were going to say something.
No, just seeing what's going on back there.
It's baby. Two babies. We've done most of the big questions because we'll be at the clinic too.